Afternoon session, and we will have the second part of the lecture by Professor Barbu on maximal monotone operator application.
Well, so continuing in fact with what I presented in the first part, we are considering here the time-dependent case. That means this differential equation, AT/YT, let's take, okay, equal 0, Y0 equal Y0, and with a stochastic analog, dx plus ax dt equal dwt, x0 equal y sub 0. In fact, last time we saw that this problem in time-independent case is well posed if A is M accretive in a Banach space. So we have a complete existence theory in the case when A is not dependent of time. Unfortunately, this is not very useful for stochastic equation, because in fact, in order to, if you reduce this stochastic equation by transformation x minus w equal y, we are reducing this equation to y prime plus a y plus wt equals 0, might be multi-valued, y0 equal f sub 0. And this equation, in fact, is exactly of this type here, where at, it is aty, it is a y plus wt. So in fact, we should look for condition under which problem 1 is well posed. Well, time-dependent Cauchy problem, linear or nonlinear, is quite a difficult subject, in fact, because we still do not have a complete theory of Cauchy problem even in linear case. But discussing of nonlinear case here, we have, however, the following result about equation 1 under the following condition. First set of condition is the following: for each t, at is M accretive. I explain what this means. And resolvent lambda plus at minus 1 with respect to t, and for each x is Lipschitzian or locally Lipschitzian with respect to t, is Lipschitz in t. Roughly speaking, this is this condition. This is not convenient, of course, because this condition resolvent to be Lipschitzian in t clearly is not satisfied due to the presence of wt in this equation. So this possibility should be ruled out. This is the first. There are many variants of this theorem, but roughly speaking, all assume that this function t goes to resolvent lambda e plus at minus 1 is Lipschitzian. Lipschitzian also is bounded variation, which precludes, in fact, an application to stochastic case. Second type of result, at is a subdifferential in mappings. That means it's subdifferential of some lower semi-continuous convex function phi, which in a Hilbert space, but is not important this, of course, where phi satisfies this condition, phi ty less than phi sy plus L t minus s y plus phi s y for all t greater than s. Okay, this condition is better than this one, because the first condition implies that the domain of at is independent of time. This not, but this still is not applicable for stochastic equation for the same reason, because even if a here is d phi, okay, wt is not with bounded variation, so also this condition is not good for stochastics. Remains the third category of hypotheses about A, which are quite good. Which is this? this is a Fouling. Suppose that we have a pair of Banach spaces, reflexive Banach spaces, V and H, V included in H, included in V prime, with topological and dense inclusion. And suppose that AT is a monotone operator from V to V prime, demi-continuous. Demi-continuous means that it is continuous from strong topology to V and weak topology of V prime, and which satisfies the following condition. In fact, two conditions. ATUU scalar product greater than alpha norm of U P V minus or plus gamma, and ATU V prime less than some constant C U V P minus 1 plus U1. Under this condition, problem 1 has a solution Y in LP0T V with derivative dy dt in LP prime 0T V prime, and also this is continuous with a value in H. Well, this is good because, for instance, you can check this condition for the operator A if assumes that A is an operator from V to V prime. We satisfy exactly this condition as time-dependent operator. And if you assume, of course, that WA, or W, it is in LP0TV. So under this condition, this theorem can be applied to our case.
Don't you need monotonicity as well for the AT?
Excuse me?
Don't you need also monotonicity for I of t because the new conditions now?
Here is monotonicity also. Monotonicity. I said monotone. Yes. Without monotonicity, nothing works, of course, because yes, it's monotone. Yeah.
Excuse me, for the first condition, which is upstairs there, which kind of dependency in T do you need?
Measurable, to be measurable.
Only?
Yes. Measurable, it's enough. In fact, it suffices that AT goes LP0TV in LP prime 0TV prime. So measurable is enough. Yeah, sure. Okay, so this is good. In fact, this is an old theorem. An old theorem of Lyon's. We can found already in first book by Lyon's, Edition Jean, Equation Opérationnelle. No, it's very good, this theorem, because it does not impose any condition about the domain and regularity in T. And this is a reason you can apply for stochastic equation. For instance, this equation applies. Okay, from here we find perhaps the first existence result in stochastic equation, result of Barbu. Result of Barbu can be found from this, exactly from this theorem. Okay, Barbu proved it by using a Lurken approximation and so on, but of course, something else. But follows exactly for here. For instance, it can be applied to this situation. AU equal minus divergence A gradient Y, this parabolic, this elliptic equation, where A is defined from AD to AD, such that I is monotone, continuous, and IU U greater than alpha norm module U P minus C, and AU less than alpha 1 U P minus 1 for P greater than 1. From here, it follows you get existence for the corresponding stochastic equation here, where the operator A is this divergence free. Now,
But in Barbu, I think his noise was multiplicative. There was nonlinearity.
okay, we are discussing here everything in the additive noise, because everything from additive noise you can apply fixed point argument and get, yeah. No, everything is no. I do not, I do not compete with the Barbu theorem. Of course, it is correct. No, I am discussing here only additive noise, okay, because otherwise you cannot reduce this. Good. So this applies to this. This also applies to this theorem. In this case, B is a space W01P. We can apply also with this theorem. A equal minus delta U plus beta U, semi-linear parabolic equation. But in this case, beta should satisfy a condition, similar condition, beta U, U greater than U, P alpha plus C, with sublinear something C, U, P minus 1. And if you take the space V to be H01 intersect LP, We can check that this condition is satisfied in this case, but you should assume that P in dimension 2 is less than 6. Okay, so roughly speaking it works, but it's not the best result. This is not the best result. In fact, the fact that we have the same P here and here is not very convenient in many applications. So we are going now to extend or to present an extension to this theorem which applies well to stochastic equations. For instance, if we want to apply this theorem here, we should assume that this P is less than some constant which depends on space dimension. So which is a theorem? Okay, is this one. We have, and also we present not only a more general result than this, but also a new approach to this type of problem. Because roughly speaking, we'll prove that the solution to our equation 1 can be obtained by variational principle. This is, so, suppose that AT is the following. Suppose that AT is d phi t, ATU is d phi t u, where phi is a function from 0 t times v in a bar convex, the function phi is convex, measurable in t, and satisfied also the following condition. Phi tu is less than some gamma 1 plus alpha, gamma 2 plus alpha 2 norm of u p2 in v greater than gamma 1 plus alpha 1 u v p1, where p1 greater infinite less than 1. Here, d phi is subgradient of phi, subdifferential of the function phi. Okay, if phi is differentiable, this is exactly the gradient. After all, it is multivariate. So AT might be multivariate. Which is a theorem? Theorem 1. Under which condition? For each f in LP2 prime, 0t v prime, there is a solution. Y in LP1, 0 tv, with dy dt in LP2 prime, 0 tv prime, which satisfies, and also y is continuous in C0th, which satisfies equation 1 almost everywhere. The difference between this one and this is we do not have the same P1 and P2, and this parameter allows, in fact, to use, we have several possibilities here. This is the first theorem here, but we assume also that phi, it is convex, and d phi, AT is d phi, so we have a subpotential Cauchy problem. Theorem 2 is a version of this one. Suppose that instead this condition here, we have this, that phi t u is greater indeed than gamma 1 plus alpha 2 u v p1, but also that phi t u goes to phi, is bounded on bounded subset of V. So it's not necessary, no longer necessary here to have polynomial estimate on phi. Phi in principle should be continuous, but bounded on bounded subset. Then we have the same result, but in this case we get that the derivative dy dt is in L1 0t v. This is a variant, I think a version of theorem 2 under a little bit more general conditions. So phi is not polynomial as regards its growth. It has only is bounded by a polynomial function. But in this case, of course, the solution is weaker. So, but still, it is a strong solution to the equation. And okay, what about the proof? And after we'll go to stochastic equation.
Scusa, ma in T che condizione c'è nella 3? In T.
Dove?
Semicontinuo
Where?
vuol dire in X, in T che condizioni c'è?
Where? Here?
Conditions are in T, depends.
Measurable, measurable. I
Only
said.
measurable.
Yes, measurable. It's enough to be measurable, yeah. Okay. Now, let's say a few words about the proof of theorem 1 and theorem 2. The proof is the following. In fact, it comes from a variational principle discovered first by Bresis and Ekeland. And unfortunately, it was not very successful to Cauchy problem defined in a Hilbert space, but works very well here. Which is this principle? We start from this equation. Y prime plus ATY equal F. Y0 equal Y0, where AT is d phi t. It's a subdifferential mapping. And we use this conjugation formula. Defined phi star is a conjugate of phi, Legendre conjugate of. That means phi t. P, it is sup scalar product Py minus phi ty. Here's duality. Then we have this nice formula that V belongs to d phi t u if and only if phi t u plus phi star t v equals scalar product uv. This is equivalent. This is a very nice formula because it reduces this equation here to the following one. Phi t y plus phi star t f minus y prime equal y f minus y prime. Almost very well. Good. Now, so we have this always, and the difference. Okay, so we are lead to the following minimization problem. Minimum integral 0 t phi ty plus phi star t f minus y prime minus y f minus y prime dt. Minimize this function for all y in LP, in our case 0, LP1, 0 tv, and y prime in LP2 prime 0 t v prime. Problem P is equivalent with this. Problem P is equivalent with this. This is famous Ekeland. In fact, it's a conjugation formula. It's in fact, it comes from the conjugation formula. It allows to reduce this Cauchy problem to this minimization problem. It's a convex minimization problem. This is nonlinear equation, but this is a convex minimization problem. This can be written in the following form. P is equivalent with the following. Minimum integral 0 t phi ty plus phi star t f minus y prime minus fy dt plus, if you integrate, norm of yt square in h. Okay, you can put minus 1 over 2y0, but this is fixed, of course. So we are lead to this convex optimization problem. In order to prove existence here, it suffices to prove that it has a solution. This is not trivial in general. It's not true always. We need our assumption. Denote this function phi y, this function integral 0 t phi ty and so on. We put here. Consider this function from phi from LP1 0 t v to a bar. A bar means that we accept plus infinite. And problem P is exactly minimization of phi. In order to have a solution for phi, you should check two conditions. Phi to be lower semi-continuous, convex it is, and to be coercive. That means we should check that phi y goes to plus infinity when norm of u in LP1 0 TV goes to plus infinity. Both conditions are satisfied in our case under assumption of theorem 1. From here, it follows existence. Well, it's not so trivial, because we should check that, in fact, the minimum solution to this minimum is unique, because the functional phi under our condition is uniformly convex. We have a unique solution, and it is something you should use some duality argument, in fact, to prove that the minimum of this solution, it is indeed satisfies this almost everywhere. But that's all. In the case of theorem 2, we do not assume in this case that phi is bounded, no, upper bound by a polynomial. We are doing the same thing. We are doing the same thing. You see, because here coercivity in fact follows from the condition we have about phi. This follows coercivity. Our semi-continuity follows from the condition we have about phi star. Because if phi satisfies this condition, phi star will satisfy the dual, the same type of condition, but replacing exponent here. Here will be u p1 prime v prime, and here will be u p2 prime v prime. So we need both, because one implies lower semi-continuity, in fact. It is this one, and this one implies coercivity of the functional. In the case of theorem 2, is the same argument, of course, but we should work in this case with y prime in L1. It's a little bit more complicated, because in order to prove that the functional is lower semi-continuous, you should invoke Petit's theorem about weak compactness in L1 spaces. But after all, everything goes through. Now, this is, in few words, the proof of the result. Now, let's see what we get from this true theorem. Yeah. Let's take a few standard stochastic equations to check this condition and what this implies. Okay. So examples. Well, the first example, in fact, okay, let's begin with the first example I mentioned. Example 1 is exactly the standard equation. Dx minus divergence a gradient x dt equal dw. Of course, w has a trace, is not exactly a cylindrical. But anyway, this is not important. In fact, the w is a process or not. You can take also a Cadillac process, something else. It's not important. It should not be. But you need some. You need some condition, because, for instance, if you apply theorem 1 in general, the condition we have, in fact, is this: we must have the w belongs to LP1 0T V1. This is a condition we need. If you apply theorem 1 to our stochastic equation 1. Okay.
You mean for each omega? You mean for each omega?
Yes, or for each omega, yeah. For each omega, of course. For each omega. This is almost everywhere. You see an omega. See, of course. We are working only with stochastic random equation associated with this. Yeah. Okay, so first example is this equation here. x0 equal x. A gradient x equals 0 on the omega. In this case, of course, operator A, it is minus divergence ay minus divergence ay. this is defined from the space V1, V, okay, equal W01 P 1 omega to V prime, the dual Sobolev space. And if you apply exactly theorem 1 to stochastic equation, reducing this to equation in y, condition about y as the following. Suppose that A is a subgradient. Suppose that J it is greater than alpha P1 plus gamma 1, and DG it is less than, here it is less than alpha 2 P2 plus gamma, and continues. But this implies that you have a unique solution, of course. P1 should be greater than 1. So we have a unique solution for the equation in y, which satisfies our condition. Now, of course, about W should have the condition here. Here it is a critical situation, P1 equal 1. This is ruled out. P1 equal 1 is very important, because P1 equal 1 is a singular, in fact, parabolic equation. For instance, equation like this, dx minus divergence from signum gradient x dt equal W, or put so, is not accepted by this theorem. Okay, but this case was treated, in fact, in a joint paper with Giuseppe and Michael Wegner. And in this case is not covered by this theorem here, but however, we have also in this case a weak solution, which is also unique, but is not covered by this theorem. It's a singular situation. Okay. Example 2. Yeah.
What do you retain exactly from the Brownian motion of the pathwise level? So, where does it intervene? We discussed a little bit.
The condition we have about W in general is this one, in all the situations here.
Okay, so any path which fulfills this?
Yes, it's almost everywhere in W, in omega. Yeah, this is the condition. Okay, example 2. Of course, if it is not for a noise, you should put some, you should take some color noise, in order to be satisfied, but you need some. Okay, example 2. Example 2 is a famous porous media equation. It is dx minus delta beta x dt equal W. I want to say that everywhere beta might be multivalued. I put equal, but in general we have belongs to, because beta also in previous case could be multivalued. So this equation, x0 equal x, beta x equals 0 on d omega times 0 t. In this case, we apply this where beta it is dj r, and j satisfies this condition, less than alpha 2 plus gamma 2 plus alpha 2 a p2 is polynomial. Gamma 1 plus alpha 1 a p1 j. Okay, in this case, we apply theorem 1 for h, the space h equal h minus 1 o, v, the space LP1 O, this is a domain, and V prime, well, V prime is not LP1 prime, of course. It's a dual of LP1 with respect to duality induced by H minus 1. So it is quite a large space to the right, but we don't care. Applying this result here, we get, of course, the following result, that that if W belongs to LP1 0t times O, and if P1 is less than P2 greater than 2D, D is a space dimension, D plus 2. If D greater than 2 and P1 greater than 1, if 2 equal 1 or 2, if D equal 1 or 2, then under this condition we have a solution X in LPW P1 0T LP10, okay, and continues with value in H minus 1. Okay, so we have in this case a condition of this type between P1 and P2 of this type 2T over T minus 2 over T minus plus 2. Yeah. This comes from Sobolev's theorem, in fact, from Sobolev embedding theorem. Okay, I want to say that this equation, we have better results than this. We have better result, in fact, because we proved already, in fact, in the joint papers, Giuseppe and Michael, existence result in sequence under more general condition. Exactly this condition is a little bit, in fact, it can be weakened, this condition, and we'll speak about this, how to do this, but not now. No? But anyway, here we can get immediately an existence result for this stochastic equation, porous mid equation, which covers quite a large class. For instance, beta equal Im, even is a classical example of porous mid equation, or if beta is Lipschitzian, is Stefan two-phase problem, and so on. So all these situations are covered by this theorem. And you can take also B dependent of T. You can take in this equation B dependent of T. Nobody forbids us to take B, because as a general theorem here, it is for AT. So we can take B, a family of graph BT, satisfying uniform in T, the condition before. Now, okay. Now, let's come back to the, well, let's come back to semi-linear parabolic equation. So, example 3, dx minus delta x dt plus beta x dt dw. Initial condition, of course, and x on boundary equals 0. Okay, there is the standard result about this semi-linear parabolic equation, of course, in the books by Jerry and Giuseppe and also Giuseppe. And usually they ask about beta, the B monotonicity, and polynomial growth. Okay, polynomial growth. I want to say that this comes exactly can be covered from theorem 1 I mentioned before. Beta here could be, might be multi-valued. Now, because we have two possibilities here to transform this equation, to put this equation into equation of this type, an equation of form 1. For instance, if you introduce here stochastic convolution integral 0t semi-group generated by Laplace operator Ws, then this equation is reduced to yt minus delta y plus beta y plus wa. 0 with standard condition, initial condition is 0. Okay, so it's nothing to do except apply for this equation here to this case. In this case, at y is this operator minus delta y plus beta y plus wa. Okay, beta, if it is monotone, it is always a subpotential. It is a subdifferential of some convex function. Now, and the condition we have in this case, is the following. Okay. Assume about beta or about j, that j are, like here, it is less than gamma 2 plus alpha 2a p2 greater than gamma 1 plus alpha 1 a p1 for all a, where p1 less p2 infinite greater than 1. Then, if w is assumed to be in LP1 0t h01 intersect LP1, this is a condition, we can apply the theorem, and get a solution x, coming back to x, in LP1 W 0t h1 0 intersect LP1 and continue with value in h. This time you apply theorem 1 for v equal h01 intersect LP1. Okay. But we can find condition under which this condition is satisfied, stochastic convolution, no? So we get existence for all beta, singly valued, multi-valued, but with polynomial growth. We'll see, but next lecture, next talk, that this condition is not necessary. In fact, we'll prove that the same result remains true if beta is a general maximal monotone graph, continuous, not continuous, everywhere defined. So this assumption, polynomial growth assumption, is no longer necessary. But in order to get such a result, you should use a sharper argument. It's not enough, because it's clear that P1 equal 1, or that this growth condition is given by the argument, variational argument. But you can develop a variational argument which permits to prove the same result in general. So, anticipating the result, I want to say that this theorem is true for every maximal monotone graph, everywhere defined. This is so. Might be multi-valued, might be never mind, might be a continuous function, monotone. So beta could be everything. You should have some jumps here, for instance, so on, but it should be everywhere defined. But here, at this level, the result follows for polynomial growth. This is the first application, no, so no other, no. Well, here is a problem, another problem. We assume everywhere here that beta and respectively j is everywhere defined. Maximal monotone graph, beta is everywhere defined. So, but what happens if beta, that means what happens if in this equation this graph beta has a domain, an interval, or a domain in an interval AB that is not everywhere defined. I want to say that in stochastic and in the deterministic case, this problem still has a solution. It's a reflection problem in deterministic case. For instance, an example. What happens if beta r is this graph? 0 if r is greater than, okay, r, let's say, and not defined for r less than r. This is an obstacle problem or reflection stochastic problem. Okay. is a case when A is 0, B is plus infinite, we have only one existence result due to Ioan Barbu from 91 for this problem here in dimension 1. In dimension 1. If W is not colored, it is a in general. I mean, what it is not. It is a when the trace is not infinite. So in general, for a Gaussian or for a linear process here, only d equal 1 we know that we have existence. Now, in general, if W has some trace properties, in fact, or some, now we still have existence, but existence is not in, we do not get a strong solution, but you get a weak solution, because roughly speaking, here appear some measure mu with a support is a compact. So reflection problem in principle can be, it is of the same form, but the difficulty with reflection problem is that if phi has a domain, an interval, phi star in this case, for instance, I take an example. Why is difficult reflection problem? Let's take the case when phi y, for instance, it is simply this function. It is 0 if y is less than v is less than rho, and plus infinite otherwise. This is still a convex function or semi-continuous on the space V. Phi star in this case is a norm, dual norm. Phi star V is rho norm of V prime. If you try to solve the problem, that is, to solve this minimization problem here, we are led to consider this problem. Which one? Minimum integral 0 t phi it's like here phi t y. This is not phi, it is not, it is norm of y prime minus f v prime, okay, dt minus f y dt for y belongs to some interval a for y less than v, 0. Okay. This problem is not well posed in the space W110 TV prime because this function is not lower semi-continuous. It is the same thing when you are trying to minimize the energy gradient, for instance, minimize this energy. This problem, minimize this gradient, is not a well posed problem in the space W11. We should work in the space of function with bounded variation. The same thing happened here. If you want to solve this problem to prove existence, we do not get a solution with y prime in L1. Simply this does not follow. But follows a solution with y prime a measure. Y prime a measure, that means that in this equation here arises a singularity. So this is in fact the explanation of the fact that obstacle problem or reflection problem, in fact, the difficulty of the problem, and also that in this case this equation becomes very singular, in fact. So unfortunately this approach excludes or precludes the case when phi is not everywhere defined, but in the general case, so everything it works well now. So this is in fact the problem, the approach I propose for this for our stochastic problem. I want to say something else here. Into this form here, or problem here, this is a very familiar optimal convex problem. We can get the solution by the method of convex optimization. In general, a first order differential in general. Almost always a first order differential equation is not a problem, operational problem. It can not be written, but in this situation, in this approach, in fact, we get the solution by minimizing a certain convex problem. So this can be advantages, in fact, even for stochastic equation, because it is an entire machinery here of convex optimization which can be applied into this case. Because in particular, you can say that the solution to stochastic problem can be obtained in the same manner. It is enough to replace y by x minus w, and everything goes. So what comes from here? Everything, all the kind of, well, you can take all the standard result of convex analysis, of convex optimization, that means convergence, graph convergence, and so on, which automatically are transmitted, are transferred for stochastic equation, for instance. Cathode-Rotor theorem, for instance. But everything is a case when A is a subdifferential mapping. Is a case when A is d phi. Well, this is quite general because many problems, stochastic problems, can be written to this form. However, it is not always true. What I mean, not every stochastic problem is of this type. Now, for instance, if you come back to our problem, example 1, if A so a stochastic problem, to be more what I'm going to say, and perhaps with this let's so coming back to this stochastic problem, dx plus ax dt equal dw. Not every problem of this type can be written, or for not every operator A, we can find a space V enclosed in H such that this one to be continuous or demi-continuous and monotone. There are many examples this does not happen. One example is a even reflection problem. But the other example as well, for instance, in the case when, let's take example 1, if AR satisfies this condition RP for P greater than 1, it is okay. We can find the space W is 0, 1, P. But if AR satisfies this condition for P equal 1, we cannot find a pair of space V, H, V prime such that A to be continuous from V to V prime. So it is not of a rational form, I'd say. The same thing happens for semi-linear parabolic equation. But here it is a problem, in fact. We have used mainly the space LP1. In all the problem I mentioned before, condition about, we put about beta, where that beta has some polynomial growth. Why? Because you looked for space LP1. There is one possibility here, to work with Orlich classes. In this case, you can a little bit extend this result. So no polynomial growth, but we still need some growth. So, and anyway, this approach do not apply to the case when beta is simply continuous and monotone. Because you cannot put any growth condition, I mean from below to beta, yeah.
So, which is the framework in which you can study reflection SPDEs with a framework of monotonicity?
Directly by using a seed approximation. Is exact. Also the first approach by Viorel Barbu is the same. But in dimension 1 is special because in this case you can use also some monotonicity. I mean monotonicity argument in the solution. The approximating solution is monotonically increasing. This is essential. But their argument do not work in dimension 2, 3, and so on. Yeah. But if you put some more condition about W, not to be okay. Have in general. you have in general. But the result, it is for W, a Brownian processing, Brownian, or a stochastic.
At the end, you don't find absolutely continuous function.
No, you even, even with this. Every time you're working with reflection problem, we get a measure here. Here we get a measure. Is a measure which is localized with in the constraint set, okay, and singular part is localized on boundary.
Is that the good spaces are not identified?
No. Well, the good space in this case it is BV, the space of functions bounded variation. But unfortunately, this is a very bad space. No reflexive and so on. It's dual. Let's forget it. So okay, you can consider it is itself is a dual. But in fact, the problem was not yet studied in more detail. No. But anyway, we have a good variational approach because this exactly what I mentioned here. It is a variational approach also to stochastic equation. So roughly speaking, if nonlinearity has some polynomial growth, a stochastic equation with additive noise can be obtained as a solution of a minimization problem. This is a conclusion, in fact. And we have quite good solutions. The solution is strong. Because in all situations, what I mean by solution? Beta, of course, x, wp, and this beta x belongs to LP1, 0t, v2 prime. So we have a strong solution in all these situations. Quite a good solution. Yeah?
Yeah, don't you get blow up with polynomial growth?
Excuse me?
You get blow up with polynomial growth.
No.
Because you have monotonicity.
No, we have monotonicity in this case. Okay. Yeah, monotonicity, no. It is pretty broad.
Yeah,
No.
well, okay.
We have global solution of problem. Yeah, sure. Yeah. No. And as I mentioned, in fact, it remains the case I want next time to discuss this equation. Is a case when beta is monotone and continuous, and says the same thing what happens with porous media equation under the same condition. Because for porous media equation about beta, applying this result, we can impose polynomial growth on beta. Is a paper by Wang and Michael, where they impose only a weaker condition, if I remember, but coming from the same variational principle, not this one, a different one, but using Orlich classes. No? But next time I'll present a general result we have here, when beta is generally, like here, a monotone and continuous function. Also for porous media. No. In this case, you cannot use this argument. You should use sharper argument. That means is the same variational approach. We transform the problem in a variational approach or optimal control problem. But in order to prove law of semi-continuity and coercivity and so on, we should use some sharp result of real analysis in a certain way. For instance, Petit's theorem and passing to limit in L1 topology and so on. Okay. But I'll stop here.
Thank you very much. Maybe there are some questions. Professor Barbu, are you preparing notes?
Excuse me? Yeah.
Are you preparing?
Yeah. I have some notes. If somebody wants, I can give it. I put down all this.
Okay.
Only give me. I will give me the email, and I'll send it. Yeah.
I wanted to ask, will you include later the case of multiplicative noise in this framework?
The multiplicative noise is a problem here because you cannot simply reduce to a random deterministic case, except some few situations. Where the noise is finally dimensional, or finally some Brownian motion. So, well, roughly speaking, cannot be reduced. But my argument in this case, to use fixed point, of course. Starting from additive noise, yes.
Even more, do I understand well that the noise must be in V,
Yes.
not simply in H, which is usually
in the variational set.
The noise here, in fact, the noise here, to speak correctly, is this part, is an operator WV. This means it is something, in fact, mu e, a basis b beta I, such that this mu I is sufficiently good to have convergence of the series. Yes. This, but I put, I think, so it's not a noise. It's not a Brownian simple cylindrical Brownian motion. Yeah.
Once again, the noise in your approach, it seems to me, must be in V, that you could do your transformation to the...
Yes, that's right. This condition I put, in fact, it is, I wrote somewhere.
Yes,
in fact, it is in LP1, 0T, V. Yes, yes, it is in V. Well, it is quite regular. Should be a little bit, it should be regular, yeah.
But you use also stochastic convolution.
In stochastic convolution is the same condition about stochastic convolution. WA should be in LP01, which is better. Which is better. It's more regular stochastic convolution than noise. But should be in LP1. In fact, I put here that W stochastic convolution should be in LP1. Yeah, it's somewhere here. Yeah.
Stochastic convolution is over there.
Yeah, the condition is the following. W should be in LP1, 0T, V, which is LP1 intersect H01. Okay, this is the condition.
Erika?
I wanted to ask about the reflection. Usually you can use also penalization methods.
Yes, this is a seed approximation. Penalization method is a seed approximation, yes. Yeah, no, it can be treated also in this way, a parallel way. Yeah.
It coincides with your seed approximation.
I don't know, because I didn't develop this. I didn't develop this, that means reflection problem in this case. Here I only mentioned that in principle would be possible, but I didn't check all the details. Yeah.
In Ioan's book, he
It's deterministic case.
yeah, but I
It's equivalent. It's equivalent. Yeah, it's equivalent. Yeah, everything for a nonlinear equation, for differential equations of a subgradient type or monotone type, you can use your seed approximation, which is penalization, or you can also use directly. Usually this is a method, in fact this is by using seed approximation. This is a penalization. Yeah?
When you mentioned reflection, it seems to me that somehow convexity plays a role. So if you consider a problem in where solution is vector-valued function,
Yeah.
and you want to reflect it against a surface which is not really convex.
Well, this is much more difficult, in fact. No, if you do not take constraint set to be convex, the problem in this case is nonlinear. It's not convex. It's I don't know exactly what happens. It is should be. Yeah, but already the convex case. Already the interval constraint is very, very difficult. It's not completely known at this moment.
More questions? So thank you again.
Thank you.